good. So in the first part of this class, we are going to use a particular differential equation, particular partial differential equation, as an example of our numerical schemes. This is called the convection diffusion equation. I'm going to write it down. So the convection diffusion equation is partial u partial t plus a capital U. So that's a constant, while the small u is a function of space and time, times partial u partial x is equal to a kappa times partial square u partial x square. Okay, so this is a partial differential equation because, of course, I'm writing partial derivatives. But also, the solution u is a function of not only time but also space. So u is a function of x and t, a function of two variables. That's where the partial derivatives come from. And I think like 90% of you knows how to solve ordinary differential equations. But how to solve partial differential equation is what we are going to teach in this class. So we are going to start with this differential equation, which is linear. And I know some of you want to solve nonlinear equations. That is going to come in the finite volume part. In finite difference, we are going to focus more on solving linear equations. And why is this a linear equation? How many, can somebody tell me why this is a linear equation? Yes?
Because if you take two solutions, you add them, you get a solution.
Very good. That's the best answer I can expect. A linear equation satisfies the following criteria. If you have two solutions to this differential equation, you add these two solutions up, it is still a solution to the same differential equation. Okay, if you have u1 and u2, both u1 and u2 satisfy exactly this differential equation. If you add them up, they're still going to satisfy the same thing. For example, if I have small u onto here, then it is a nonlinear differential equation, because if you have small u1 and small u2, you add them up, they no longer satisfy the same equation. Okay, but if I have a capital U that is a constant here, it is a linear equation. Okay, good. So it is a linear equation, but it does model a lot of things in science and engineering. And here I'm focusing a lot on engineering examples. For example, in thermal engineering, we are usually concerned about the evolution of temperature. For example, we don't want things to melt, we don't want things to freeze or burn. So here, the small u would model the temperature of like in a fluid or in a solid. In environmental engineering, we are concerned about the concentration of pollutant, or when there is a building fire, the concentration of smoke, let's say. And in this case, the u would model the concentration of a particular species or something. In petroleum engineering, the same u can model the fraction of oil or fraction of water in an underground reservoir. And in financial engineering, you can use the same differential equation to model the price of an option. So there is a lot of applications of equations like that. And in particular, we are going to solve this equation with boundary conditions. The boundary condition says that the solution at a particular x and a particular t and time is equal to, let's say, ul of t. So we are solving this on the domain of space and time. So let's say this point is L, this point is R, and we also have u of R and t is equal to ur of t. So we know the solution on this line, we also know the solution on this line, and we also given initial condition. That is u of any x and t equal to 0 equal to, let's say, u initial of x. So basically, we are given the solution on the boundary in space, and also in the initial time, so t equal to 0 and x equal to L and R. And we are asked to solve for the solution within this domain. This is a typical setup for a partial differential equation in space and time. Okay, so why we are going to use this differential equation? Because this differential equation, we have a very good feeling of how it behaves. So let me switch to MATLAB. Hope I have MATLAB open already. Okay, I think you can see that. And I'm going to do a simulation of this convection diffusion equation with a particular u and particular kappa. So let's say I'm going to use a u equal to 1.0 and kappa equal to 0.01. Okay? I need somebody to come up and help me draw an initial condition. So this time I'll ask somebody in the front. Could you please come and help me draw something? So can you use that pen to draw a line on the screen that represents the initial condition of my convection diffusion equation. It goes from left to right. All right. Very good. So now we are seeing a numerical solution of this partial differential equation in action. And in this case, our boundary condition is so-called periodic boundary condition, which means my u at the right, which is actually 2 pi, is equal to my u at x equal to 0. And my u at x equal to 0 is equal to u at 2 pi. So we basically have a periodic domain that is on which we solve the differential equation. And the initial condition is drawn by, what's your name?
Raphael.
Raphael, okay. So the initial condition is drawn by Raphael, and we see the evolution in action. And if you look at the title, we have time evolving. All right. So anybody wants to see the solution at a different kappa and u? Anybody?
Try a negative u.
Try a negative u minus 1, is that fine? And kappa?
Negative 2.
Negative 2, okay. Could you please come and draw initial condition? Oh, can you draw from left to right?
Oh.
Sorry. Oh, I think this is. Let me restart it. Oh yeah. Okay. All right. Could you go from left to right, please? Ooh. Okay.
Okay. I broke it.
So the solution blows up, and the reason is kappa is negative. So that is when the differential equation is not well posed. I think I get a bunch of infinities or something like that. So that's a very good lesson. So when kappa is negative, the equation is not physical. And if you studied the analytical partial differential equation, you're going to find out the solution can become ill-defined at finite time. And that is reflected numerically by the solution going into infinity or none pretty soon. And you're going to find, I'm sure you're going to find this happen when you are coding up something. See a bunch of infinities and nons, and how to debug infinities and nons is one of the things you are going to learn, I hope. Anybody else wants to try some convection diffusion equation? A different combination of parameter? Yes?
I would try a large kappa. So -1 for u, maybe 20 for kappa.
20 for kappa. Okay. Could you please come up and draw an initial condition? From left to right. Okay. There we go. All right. Good. So the large kappa means a large dissipation. I mean, dissipation is the force that makes things equal. So what we see is that the solution, although is drawn initially very weakly, it gets damped out to almost a constant very quickly. Okay, anybody wants to try something else? How about a negative U but still a small kappa? How about a 0 kappa? Okay, you want U also to be -1 or something different? Huh?
U is -1 is fine.
Okay. Do you want to come and draw again to see like a working?
Break it again.
Come on. All right. So this time we have 0 kappa means 0 dissipation, no dissipation. And U is -1. And how is that different from when U is positive? Direction, right. So the advection term is what makes the bulk of the solution go in one way or another. A positive U makes the solution go towards the right. A negative U makes the solution go towards the left. And because there is no dissipation, the solution stays like the same shape as it is initially. It just goes towards one direction. All right. So why do we look at this equation? Because it's very easy to understand the correct behavior of the solution. U positive, it goes towards the right. A large U goes towards the right faster. A negative U goes towards the left. A more negative U goes towards the left faster. And kappa, if it's negative, it blows up. If it's positive, it dissipates the solution. If it's 0, it keeps the shape of the solution. So we have very good understanding of how the solution should look like. Okay, and so when we implement a numerical solution method, we can check the numerical solution against our understanding of the behavior of the system. Right, that's a very useful tool. If we start from the Navier-Stokes equation of turbulent flows, maybe that's even we get a solution, we don't really know if it's correct or wrong. Okay, we are going to apply finite difference, finite volume, finite element, and boundary element to equations like that.